Okay, so today I start chapter 7, that's systems of first order differential equations. Now I will start with an example, which is in fact in your book, an example from vibrations. Suppose you have two masses, M1 and M2, and they are connected, and this is a wall here, another wall here, and they are connected with three springs. This one, this one, and this one. Without the middle one, then I have just two separate systems. But the middle one is connecting those two systems. So this connection, we will see in equations down here that these two x's, x1, x2, will be in both equations. So that is what we call a system of equations. Now this is, you will see this is not the first order, but this is an example of a system of differential equations. Okay, so let's see. Now what is the input? The input here, the system is this. The input is F1 and F2, and the output or outputs are in fact X1 and X2. So two inputs to the system and two outputs, and to some extent they are acting on their own, but because they are connected with this, they are restricted to some extent. So anyway, equation of motion is this: m dx squared dt squared is ft, and we assume that the forcing function is in fact a function of t. So Freebody diagrams, this is M1, assuming that this is going this way and this is going this way, which I have here. Then this is like stretching, so this is like K1, X1 this way, and this, depending on whether this is bigger than this or this is bigger than this. If this is bigger than this, then the force is like stretching. So if this is going further, then it is stretching, and how much? It's x2 minus x1. So the force is this way, K2 times x2 minus x1. If this is bigger than this, it is compressing, so you will get K2 times x1 minus x2, but this way, okay? So if it's going this way, you will get this. But let me draw. So it will be K2 times x1 minus x2. But either way, we will see in the equation, they are the same, because this is minus this, right? So either it's stretching or compressing, they will show the same in the equation. Now this one also, so this force will be this way. If it is this way here, it is this way here, then the force here is the same. And then M2, and we have x2, and this one assuming that it's going this way, so this is compressing, so that's K3x2 and F2. Now, equation of motion on this first one is M1 d1 squared dt squared is this is going this way, so this is the negative and this is the positive, so this one is negative here, negative K1 x1, and this is positive K2 x2 minus x1 plus F1t, these two are positive, so they're positive here. Then this one again, this direction is positive, so M2 dx squared dt squared is, and here this goes this way, so it's minus k x squared x2 minus x1, and this is again this way, minus k3 x2 and plus f2t. So as you see, this and this are in fact in both of them. This expression x2 minus x1. So we cannot solve one of them on its own. Somehow they are connected. So and this happens a lot. Any system has many components that are connected. Somehow they're connected. They are not just autonomous components. They are acting on their own. No, they are connected. So and this connection gives a system of some kind of equation. In this case, it's differential equation. So when things are connected, you will get a system. Okay, now this is just a nice example to see that even the simplest spring mass system, when they're connected with some spring in between them, you will get an equation like this, which is coupled. So you have to solve them together. Okay, so let's erase this thing and start. So now let's write the simplest situation, which we have just two equations in two unknowns. And let's get, I mean, this one, the example had the second derivative. So let's just write first derivative. In fact, we can change this into, convert this into first order. And now these are just first order. So we have y1 double prime is a11 y1 plus a12 y2, and the y2 double prime is a21 y1 a22 y2. So this is coupled. As you can see, the y1 and y2, we'll see, this is just prime, sorry. As you can see, this is a coupled system. y1 and y2 are present in both of them, and so we have to solve them together. And there is no initial condition here. Let's just try and solve it in general. So when we solve it in general, we are in fact finding the complementary solution. But anyway, so let's see. Let's just look at this. So I have y1 and y2, and these are constants. The a's are constant. So y1 and y2 added, multiplied by some constants, gives me the derivative of y1. And the same here, gives me the derivative of y2. What kind of function can give me something like that? And you add them and you get the derivative of one of them. First of all, derivative and function itself. Remember from first order from like a long time ago, one of the functions that really works in cases like this is e to power x and its family. So it should be some e to power something x or something t. In this case, it is function of time. So that's e to power lambda t. So I can say that, okay, since they are added and I cannot have two different, say, exponential functions here, so let's just assume that they are the same. So y1 will be some e to power, usually we write lambda here, lambda t, and y2 should be again some kind of exponential with the same. But the coefficients might be different, so the first one might have some coefficient, y2 has another coefficient. If this happens, it might happen, I'm not saying it might happen in practice, but so we say this is v1 and v2, so they have two different coefficients. And since the coefficients here are constant, so we just take those coefficients constant. So let's see if, assuming that the two solutions look like this, just we plug in and see what happens. So if the two solutions look like this, in the end we will see that something should happen so that the two equations, the two solutions look like these two, exponential with the same constant over the lambda t. So let's plug. So here I have the derivative is lambda v1 e to power lambda t is a11 v1 e to power lambda t plus a12 v2 e to power lambda t. The second one will be lambda v2 e to power lambda t and a21 v1 lambda t plus a22 v2 e to power lambda t. E to power lambda t is here, 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 and also here. So I can divide both by e to power lambda t. E to power lambda t is never zero, so I can divide it by e to power lambda t, and I will get this equation. dividing by e to the power lambda t, I will get lambda v1, lambda v2, and I have a11 v1, a12 v2, and a21 v1, a22 v2. Well, you can see that this side is, it looks like a system of equations, right? So let's put it in matrix form. In matrix form, this will be a11, a12, a21, a22, and this is multiplied by v1, v2. And on this side, I can just write lambda times v1, v2. If I use, say, different, so if I say, let's use A for this, and this one, let's say V, and this one also V, so the equation in fact becomes A V is lambda V. Okay, AV equals lambda V. So this is telling me that if the two solutions are going to look like those two, then this should be satisfied. And this is known, the only thing that we know is A. This one, lambda, and V are unknowns. The only thing we can say is that if I can find a V1, V2 here somehow, then I can multiply, divide this by a non-zero number. So any multiple of V is also a solution. So this V is not unique. But how about lambda? Well, who knows? So, but anyway, this kind of equation that an operator times a vector is a number times the same vector is an example of what we call an eigenvalue problem. Eigenvalue problem. This is called an eigenvalue problem. When an operator, in this case a matrix, times V, a vector is lambda times that vector. Just look and try to just grasp the idea. This means that if I multiply this vector by some big matrix, it's like multiplying it by a number, right? What does this number do to V? It just stretches or makes it small, so it doesn't change the direction of this V. It's just at times some constant, so it gets larger or smaller. So it's like this A simply makes V larger or smaller. So it is telling me find a vector such that when you multiply that vector by A from the left, A times that vector really doesn't change. That vector gets like larger and smaller, they're just in length, say, in magnitude. So that's one way of looking at eigenvalue problem. Now there are different interpretations and different ways to look at it, more advanced and blah blah. For us at this moment, that's all we need to know. So let's discuss eigenvalues and eigenvectors. And that's where that chapter 5 of linear algebra comes into the picture. And I will discuss it just briefly. And so, in fact, this is chapter 5 of the linear algebra. So, first of all, when we talk about vector spaces, we might have complex vector spaces. So for complex vector spaces, we deal with C, which is complex numbers. C is Z, which is A plus BI, and I squared is -1, A and B are real numbers. So C is the set of complex numbers. And let's just review a little bit complex numbers. So we have Z bar, its conjugate of Z, and that is A minus BI. So just put minus, I will change the sign, So say for example minus 3 minus 2i bar will be minus 3 plus 2i, right? So it simply changes the sign of that. And if I multiply Z and Z bar, I have this thing, A plus BI times A minus BI, and that is A squared minus BI squared, which is A squared minus B squared, I squared is -1, we have it here, yeah. So that is A squared plus B squared. We add complex numbers by just adding like that, right? So A plus BI plus C plus DI, just add like that. A plus C plus B plus DI. And we multiply them by just say A plus BI, but be careful when you multiply. C minus DI or C plus DI, and that is, just do foil it, and be careful, you have a C plus a DI plus BCI plus BDI squared, and I squared should be -1, so don't leave it as I squared. So if this is -1, this will be AC minus BD plus AD plus BC. But I don't think we need more than this thing. You can just take a look and just Google and see how you divide them and so on. We just need this for certain things. Anyway, so this can be a vector space. These things can be considered vectors over either real numbers or complex numbers. That's either of them. But I'm not going too much into that. So we can have complex vectors. Say if I have Cn, like Rn. So Cn will be like this: Z1 up to Zn. And Zi's are in C. So I can have a vector like this. Okay, so I can have a vector like this, Z up to Zn. For example, say 2 minus 3i, 5 plus 6i, say, belongs to C2. Okay? And when you are given something like this, you can write it down in two parts, right? So, for example, this one you can write it as a real part 2, 5 plus minus 3, 6, 5. So it's like a vector in R2 plus another vector in R2 times I. So you see this is like a vector in R2 plus UI, right? It's like V plus UI. Okay, so, and this U and V belong to R2. So the U and the V belong to R2. Okay. Now, because we will, when I discuss eigenvalues and eigenvectors, we can have eigenvalues which are complex and eigenvectors which are complex. So they live in the complex vector spaces. So And everything else that we discussed, and most of them we discussed for vector spaces, just any vector space, applies to this, like linear independence and other things. Okay, so now an eigenvalue problem. Is given A, which is n by n, find lambda and V, which is n by 1, such that A, V equals lambda V. So lambda is called an eigenvalue of A, and the V an eigenvector. Corresponding to lambda. Okay. So eigenvalue and eigenvectors. Let me see which way does. I'm just trying to. Each author and book has different. So let me just use the convention. I will write both of them. So, and I can't remember which one the other book. So we have this A V equals lambda V. I can write this as lambda I V. And this is In, right? Doesn't change anything. In times V is V. Then I will move this here. There are two ways. One is moving it here. Lambda In times V is 0. And this is 0 vector. Or you can move this one to this side. You will get lambda In minus A times V is 0. To be honest with you, I think the book, the linear algebra book, goes this way because of the lambda, the equation that we find will the lambda to power n, there's a lambda to power n, say, and it has coefficient 1, not negative 1. This one might be positive negative, depending on the dimension, depending on this n. This polynomial here, which I will tell you what that is, might be minus lambda n or plus lambda n. Now, if you use this one, then you don't have to change the sign of elements of or entries of A. In this one, you have to change the sign of the elements or entries of A. But anyway, let's stick with this one. But be careful when you are multiplying things. Be careful. Just be good. You should be good in algebra and in multiplying, like just algebraic manipulations. So now let's see. Either of them. This discussion is true for both of them. Now, but this is what is one solution to this system? We know that this is a homogeneous system. A homogeneous system always has one solution at least, and that is 0, which means V equals 0, 0, 0, 0. But do we need are we interested in that? No. So we want a non-zero solution of this. So try to find non-zero solution. And what is the unknown? Unknown is V. Okay. Remember, if the determinant is 0, determinant of this coefficient matrix is 0, if it's not 0. If it's not 0, there's just one solution, and that's 0, finished. So if it's 0, then we have infinitely many solutions. Because we have one solution, so we either have one solution or infinitely many. And if the determinant is not 0, we will have infinitely many solutions. And that's why I said this V can be just a multiple of V. It depends on the situation. So let's see. So in order to have this non-zero V, implies that this determinant of A minus lambda in 0, in this case, it is determinant of lambda in minus A. If I remember correctly, the two books have different, they write it differently. I guess this is the linear algebra book, and this is like the differential equations book. So you will get the same answer. So that's the same equation. Okay, so this is what? This is an equation in lambda. So this is an equation, in fact it is a polynomial in lambda, right? The polynomial in lambda, determinant of A minus lambda in, and this is a polynomial in lambda. The same as here. So this is minus this. So, and it's called characteristic equation. So it's characteristic equation, name. Okay. So characteristic equation, so this polynomial, zeros of this polynomial will be eigenvalues. So zeros of this, zeros of d lambda are eigenvalues of A, of matrix A, right? The zeros of this polynomial are eigenvalues of matrix A. And when we find those zeros, then we plug in those zeros, which are different values for lambda in the equation, and we will find eigenvectors. So let's try one. So example, if I can put on here. Let me double check again. I'm not sure. Yeah, come on. Okay, yeah, this is the okay, so it is A minus lambda. Okay, so example, well, let's say A is 2 minus 3, well, let me give you right and 5, say. A symmetric matrix, and there's a reason. So find eigenvalues and eigenvectors of A. Find eigenvalues and eigenvectors of A. So we have determinant of A minus lambda I. So this is in fact determinant of this matrix. So what happens when I do this? So it is lambda I is this. Lambda 0, 0, lambda. So this matrix 2, -3, -3, 5, minus this. So this lambda is subtracted from the diagonal. The rest are stay the same. So it's determinant of 2 minus lambda, -3, -3, 5 minus lambda, and 0. So the determinant of this is 0. Okay, so let me erase this. And so that is 2 minus lambda times 5 minus lambda, minus, that's -9, equals 0. So when you multiply these two, I always do this, but you can do that. I have seen students making terrible mistakes when they multiply this. And I understand why the other book uses lambda I minus a, because then the lambdas are not negative yet. And this negative is just a hand. So I would flip both of them, and if you have 2, flip means what? This is minus this is minus this. So it is minus this times minus this. So the minus cancel each other. So this is equal to this. So just flip it. No, that's not flipping. Flipping is it's the minus of that, okay? So minus of this. So lambda squared, that's lambda squared, minus 7 lambda plus 10 minus 9. So that is lambda squared minus 7 lambda plus 1 is 0. So lambda is 7 plus minus square root of 7 squared 49 minus 4 over 2. Okay. So lambda will be, let me simplify, 7 plus minus square root of 45, is it? Yeah. Divided by 2. You can leave that square root of 45, that's okay. Or you can say it is 9 times 5, so 5, so it will be plus minus 3 square root of 5. So we have 2 lambdas. Lambda 1 will be 7 plus 3 square root of 5 over 2. And lambda 2 is 7 minus 3 square root of 5 over 2. So these are the 2 eigenvectors, eigenvalues of this A. Okay, so let's double check. 2 minus lambda 5 minus lambda, that's lambda squared minus 7 lambda. And plus 10, okay, and then minus that is plus 9, minus 9, okay. And so that is 7 minus plus 1. So I have minus 4, that's 45, and then 3, that's 9 times 5, so okay, I guess that's good. So let's go back to the equation that gave me this. Now I have 2 lambdas. I have to go back to the equation that gave me this determinant. So let me just keep these 2 lambdas here and erase everything else. So what was the equation? The equation was this. A minus lambda I times V is 0. So what is A minus lambda? A minus lambda, that is 2 minus lambda minus 3 minus 3, 5 minus lambda times V1, V2 is 0. So V1, V2 is 0. 0, 0. First of all, I set this determinant to 0. Now when I have any number of equations, if the determinant is 0, then it means that at least one of them is a linear combination of the other ones. So this means that this one is a linear combination, not linear combination, it's a multiple of this. I shouldn't have lambda that. I'm not going to show that to you, but the determinant is 0. So the theory tells me that this is in fact the multiple of this, no matter what. So I just did one of them, one of the equations. So when we have two, which most often we are dealing with two equations, at least in this class, two equations, or maybe three. So if it is 3, then one of the rows, we can just throw out the last row, for example. So I can throw one of the rows, and that's this row. So let's see. So lambda 1 is 7 plus minus, no, plus 1, that's just plus, right? So plus 3 square root of 5 over 2, and that gives me this equation. Let me erase it and write it here. So 2 minus lambda, okay. So 2 minus this guy here, that is 2 minus this thing, 7 plus 3 square root of 5 over 2 times v1 plus, minus in fact, minus 3, minus 3 v2 is 3. And I don't need the second one. And so I have to solve for v1 and v2, and you know this is an equation, which is just, in a sense, one equation and two unknowns, so I need one free variable, but forget about free variable. Just, you need just one solution, right? You just need one v. And remember, any multiple or any constant times this v is a solution. So the easiest way is to just look at this and say, okay, if I choose v1 to be 1, I can find v2. Now, it's not a nice expression, but that's okay. That eigenvector is not so nice. So depending on the situation, you can let the other one to be, so let v1 be 1, not v2, sorry. v1 be 1, then I have 3, v2 equals this guy here. Well, let me multiply 2 times 2 is 4, minus 7 will be minus 3 plus 3 square root of 5 over 2. So v2 will be, this is 3 and 3 and 3, so the 3's cancel out. I will get minus 1 plus square root of 5 over 2. So that's v2, if v1 is 1. So for this lambda, I will get v eigenvector, so that's eigenvalue, and the v for this one, let's call it v1. This is different from that v1, but let's just call it v1. Is, which one did I pick? This is 1, and this is minus 1 plus square root of 5 over 2. Okay? So that is v1 for this lambda. So that is eigenvalue, eigenvector corresponding to this eigenvalue. Okay, let's find the other eigenvector. The other one is 3 minus 7 minus 3. And we can guess what happens. So let me try. So there's a minus 3 here, right? And I do the same thing. v1 is 1, v2 will be minus 3 here. And in the end, I have minus. So if this is lambda 2, this is lambda 2, the second one, and the v2 is this. And in fact, the only difference is that this is minus. Okay, so that is lambda 1 v1, lambda 2 v2. So the two eigenvalues and the two eigenvectors. So let me erase this and summarize. So eigenvalue lambda 1 is 7 plus 3 square root of 5 over 2. Eigenvector v1 is this, and minus 1 plus square root of 5 over 2. And the other one, lambda 2, is 7 minus 3 square root of 5 over 2, and v2 is 1 minus 1 minus square root of 5 over 2. Okay. So these are the two eigenvalues and eigenvectors. The lambdas are eigenvalues and v1 and v2 are eigenvectors. Now, what is it? It's this. You can check yourself. I'm not going to check it, but you can check yourself. This A times, say, one of them, say this one, 1 minus 1 plus square root of 5 over 2 is this lambda, which is 7 plus 3 square root of 5 over 2 times the same thing. That's the meaning. We have found this vector and the lambda, and we only had one input. That was the matrix itself. Now you might say, gee, with one input we found two. In fact, this one here, the eigenvectors are, as I said and I say it again, this eigenvector can be any multiple of this. So if you don't like this 2 here, you can write v1, simply multiply it by 2. 2 minus 1 plus square root of 5. That is also an eigenvector. Most often you deal with or they ask you to write or find an eigenvector which is a unit vector. So what you do is you divide this by its norm. And so you divide this thing by its norm, and you give this as eigenvector. Well, this is, depending on the situation, this might be the best way to, the best one, or the most important one. But anyway, you can see that this is not in fact unique. The V is not unique. The eigenvector is not unique. Okay. Yeah, I guess I have time for another example. And I'm just writing an example on the fly, a 3 by 3. I don't expect to be able to solve it here, but let's write it. Just let's say we have a, let me think, what can I do to make it simpler? So I say, like say 1 minus 2, let's just write a simple number, I mean very small number, so 3 say, and this is again symmetric, and minus say 4 say here, and then this will be, oh let's just write 1. And then symmetric, this is 3, this is 1, and let's write maybe just here, right? Okay. So find eigenvalues and eigenvectors. And let me see, is it symmetric? Yeah. Find eigenvalues and eigenvectors. Okay, so we have a v equals lambda v, and that gives me determinant of a minus lambda I, in this case, is 0. And remember, when you, this equation is simply this, determinant of this matrix, 1 minus lambda, minus 2, 3, minus 2, minus 4, minus lambda, 1, 3, 1, 0 minus lambda, which is just minus lambda. Okay, so this is just a full way, except this one is 0. But so I don't expect me to solve it. So let's see what happens. 1 minus lambda times determinant of this, which is well undefined. So that is minus 4 minus lambda times minus lambda minus 1, right? The middle one is plus 2, in fact, plus 2 times this times this, which is minus 2 minus, that's 2 lambda minus 3. And plus 3 times this times this is minus 2, minus this times this will be minus is plus, so I have plus 12 plus 3 lambda equals 0. So this is the characteristic equation for this situation. Let me, how much time I still have some time before 50 minutes. So what should I do? Let me erase this and try to simplify this thing and see what happens. Maybe I can solve it. Let's hope. So I have lambda squared plus 4 lambda minus 1 inside this. And the other one is plus 4 lambda minus 6 and minus 6, is it? Minus 6, oh good, we put them together. So that's minus 10, 10. So that is in fact 30 plus 30, 9 lambda, right? 9 lambda. So this one will give them, let's multiply this, minus lambda 3, minus 4 lambda squared, plus lambda squared, plus 4 lambda minus 1, plus 4 lambda minus 6 and 30, that is 24, plus 24 plus 9 lambda is 0. So if I haven't made any mistake, let's hope not. So I have minus lambda 3 minus 4 lambda squared plus, also that's minus 3 in fact. Is there another lambda squared? No. So this will be minus 3 lambda squared. So I have rid of this one, this one, this one. Lambda, 5 lambda, 9 lambda, 18. And constants, I have a minus 1 here and a plus 24. Plus 23. 0. As you see, when you have the 3 by 3 matrix, that lambda is minus lambda 3 in fact. Let me double check my calculation. Minus 4 plus lambda squared for lambda minus 1. And which I forgot. So let's hope it's correct. So I wouldn't stay with this. So I multiply this by negative 1, so I will get this. Lambda squared plus 3, lambda 3 sorry. Lambda squared minus 18 lambda minus 23. Okay. Now I have to solve this to find lambdas. I can't see anything interesting in this, so my suggestion is use Wolfram alpha to find exact. So this should have 3 real solutions, but the 3 real solutions definitely are not nice ones. So there should be some square root of blah blah blah. So I think, I'm not sure. Maybe it can be factorized. Let me see. So, Okay, so find zeros of this. So, and you will get 3 lambdas, lambda 1, lambda 2, and lambda 3. And I'm not saying they're easy. Now I will probably show you how to do that on Wolfram Alpha or Mathematica, if you have Mathematica at home, to find these lambdas. Now, if I give you anything, well, since your exam is a take-home, then I might give you something like this, so you can do that on Wolfram Alpha. So anyway, so let's stop here, and I will write down the solution to this equation, and I will find eigenvectors for you next time. Okay, see you.